Okay, so before we get to the first law of thermodynamics, let's just go over that tutorial problem. Okay, so we had a gas doing some work and it was in an adiabatic state, right? So the equation of state is given by the following. PV to the gamma is equal to C. Okay, where C is some constant. So we will cover this later this week on adiabatic processes. And this is also in the hand-in problems on adiabatic processes as well. Okay, so you'll get plenty of practice dealing with these kind of processes. Okay, so what we want to do is calculate the work done. We want to calculate the work done going from some volume V1 to some volume V2. Right, so either compression or expansion, some change in the volume. So the work done is equal to the integral from V1 to V2 of P dV. So this is just our starting point. Whenever you're trying to work out the work done by a gas, that's your starting point. Now we know the pressure in relation to the volume is given by this equation of state. So we're going to take that and substitute it in. So if we solve for the pressure, it's going to be P is equal to C times V to the minus gamma. Okay, so we can sub that in. So this is going to be equal to the integral from V1 to V2, C times V to the minus gamma dV. Okay, now everything's in terms of V, we can just integrate as normal, right? Normal integration here. So this is going to be C times V to the minus gamma plus 1 over minus gamma plus 1. Okay, so that's the antiderivative, and this is evaluated from V1 to V2. Now what we want to do is evaluate at the upper bound and at the lower bound. So this is going to be C times V2 to the minus gamma plus 1 minus C times V1 to the minus gamma plus 1. Okay, all over minus gamma plus 1, we can write that as 1 minus gamma. Okay, now in the numerator, we've got these two parts here with this exponential, the minus gamma plus 1 and the minus gamma plus 1. We can separate that out into two parts. So this is going to be C times V2 times V2 to the minus gamma. Oh, I think it would be better if we write it the other way. Minus gamma times V2 minus C times V1 to the minus gamma times V1. All over 1 minus gamma. Okay, so why did I write it like that? Well, if we look at this bit, the C times V2 to the minus gamma, and on the other side, C times V1 to the minus gamma, that looks like what we had earlier for the pressure. The pressure was P equals C times V to the minus gamma. So C times V2 to the minus gamma, that's going to be P2 times V2 minus C times V1 to the minus gamma, that's going to be P1 times V1 over 1 minus gamma. Now, in the question, it had P1, the one state minus the two states, but that's fine. We can just take out a minus sign, okay, to swap those around and then put the minus in the denominator. So then this gives us P1 V1 minus P2 V2 over, instead of 1 minus gamma, remember we put that minus sign, so it's going to be gamma minus 1. Okay, and then that's the relationship that we needed to show. Okay, is that all right?
If we use for the work, that work is equal to negative of the integral, will it still work?
If you put minus the integral, then that's the work done by the environment. So this is the work done by the gas. So if the question asks find the work done by the gas, then it's like this, because P is the pressure of the gas pushing outwards. So this is W gas, if you want to write it like that. Or if you want to write W environment, that's minus the integral from B1 to B2, P dV. So it depends on what you asked. Okay. Does that answer your question?
Yes, sir.
Okay, awesome. There was another question here for tutorial 2.5 and 2.10. Okay, so we're going to have to save that for tomorrow's lesson, where we're going to go through the other tutorial questions. Okay, so I hope you don't mind waiting for tomorrow for that. Okay, because we need to get started on the first law of thermodynamics today. Okay, so now for the main part of the lecture today, the first law. Okay, so the whole chapter is called the first law of thermodynamics, but the most important part that you need to remember with this is how we measure the change in internal energy of a system. So we write delta U is equal to Q minus W. Okay, so I'm going to write it like this, and then I'm going to explain that sign convention again. So delta U, that is the change in internal energy. Okay, so I'm going to explain all these things. So I just want to give them names for now. Q is heat added to the system. Okay, so you can see here Q, if I add in heat to the system, then the internal energy goes up. Okay, because if Q is positive, delta U is going to be positive, and so the energy goes up. On the other hand, W, this is work done by the system. Okay, so this is something like if you imagine a gas expanding or contracting, it's pushing on the environment or the environment is pushing on it. That's that mechanical work done. Okay, and it's a minus because whenever you do work, your energy goes down. Okay, so if the gas does some amounts of work, its internal energy will go down, and so delta U would then be negative in that case. Okay, so that's just explaining what these little bits mean. In the WhatsApp group, I put a little brief explanation on that sign convention. So here we put a minus sign, and we consider the work done by the system. Okay, so if it does work, the internal energy goes down. So then this would be something like what we had in the tutorial example, integral from V1 to V2, P dV. That's the work done by the gas. You calculate that, you plug it in with the minus sign over here, just got the minus there, and then that gives you the change. There's also a sign convention where instead of the minus, we use a plus. So other sign convention. This is the Iupac sign convention. So you've heard this name before, the Iupac naming. Other sign convention is delta U is equal to Q plus W. Okay, like that. And then here, it would be the work done by the gas. That would be minus integral V1 to V2 P dV. Okay, so it doesn't really matter where you put the minus sign, as long as you understand the physics behind it. So if a gas does work, if it expands, then its internal energy goes down. Okay, that's the physical reality of it. where you put the minus sign, if you choose to use this convention or another convention, that doesn't matter. Okay, as long as you're consistent and your answers make physical sense. Okay, so just keep that in mind. I don't mind which convention you use, as long as it makes physical sense. Okay, and then from this, we can then get the differential form that we spoke about last time. So if we take this delta U is equal to Q plus or minus, it doesn't matter which one. So I'll say plus or minus, you choose your convention. From this, we can then get the differential form, okay, and that would be du is equal to dq with the little bar, okay, because remember, this could be a process function, okay, so heat is a process function, but it could depend on the path taken, so we put the little bar there. Okay, and w, we know that that's going to be p dv, so this will be minus p dv. Okay, and this is the formula that we're going to be using many times with the different examples. Okay, so sometimes you'll see the first law of thermodynamics written in this form with the delta U. Sometimes you'll see it in the differential form. Okay, you should be familiar with both of them. Okay, but we'll be using this differential form quite a bit. Okay, any questions on that?
So if we use the delta U is equal to Q minus W, then the integral where it says PDV becomes plus.
No, that's always like this. It doesn't matter which sign convention you use, there's always the minus sign here. Because remember, this minus sign from the W is hidden here. So when you take the differential, you always get that minus sign.
Okay.
Okay. So it's like hidden inside the W here. So when you find dW, it's always this PdV with the minus sign here, okay, in the blue box. Okay, so that's always there. This is not a sign convention. Maybe we can put that as a homework problem. Okay, so show that we get du is equal to dq minus p dv for both sign conventions. Okay, I think that's important to know. And remember, those sign conventions are delta U is equal to Q plus or minus W, depending on where you put the minus sign for W. So either you put the minus sign in front of W for that initial formula, and then W is the integral from V1 to V2 PDV, or you put the minus sign on the integral and then you use plus W. So you put the minus there. Okay, so either way, you get the same thing. So maybe that's a good idea to show. Okay, let's now explain what these terms are. So we already know what work done is. We did that last time. But internal energy and heat, those are new to us. So let's have a look at that. So the first one is internal energy. Okay, and that's U. Okay, so we know what energy is from like first year. Energy is potential plus kinetic. That's the total energy of the system. Here, instead, the internal energy U is given by U micropotential plus U microkinetic. Okay, so why do I say micropotential and microkinetic? Well, that's because we measure this potential energy given a particular microstate. So let's have a look at an example. Okay, so let's say we consider two atoms, number 1 and number 2. Okay, the first atom has velocity v1, the second one has velocity v2. Okay, and then there's some separation between them, r1, 2. Okay, that's the distance between them. The micropotential is the total potential energy within the system. So U micropotential would be equal to some potential between the two atoms or molecules, depending on the distance between them, plus and all the other pairwise interactions. Okay, so then this potential here, that depends on what you're working with. For example, if you've got, let's say, noble gas atoms, then they might be interacting with the Lennard-Jones potential that looks something like this. So here's V and R. If you're working with charged particles, then you've got the Coulomb potential. And that might look something like this. Okay, you know, 1 over R, or might look something like that. Okay, depending on if it's 2 positive charges or 2 negative charges, or look something like that. Okay, so whatever potential you have between the particles, you add up all of that together, and then you get the micropotential. Okay, again, emphasis on the micro part. We're only interested in what happens within the system. So if you have a box of gas, we're only interested in the stuff that happens in the box. For example, if the box is on a table, right, we know that the box has gravitational potential energy. However, we're not interested in that. Okay, we're not interested in those outside effects. We're only interested in what happens between the particles within the system. So don't worry about all those outside effects on our system. Okay, so that's the micropotential, and then the microkinetic, defined very similarly. Microkinetic is equal to 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus ... We add up all the kinetic energies, and that gives us the total microkinetic. Okay, we add these two together, and that gives us the internal energy. Okay, so just a little note on the ideal gas. So everyone should be familiar with what an ideal gas is. You've got a bunch of particles moving around, and they're not interacting. They're just moving around. They don't see each other at all. In that case, we can calculate this internal energy statistically, which we will do later on. And we get the following behavior. So for an ideal gas, the internal energy is proportional to the temperature. Okay, we'll do this calculation later. Okay, so there's some proportionality constant there between the temperature and the internal energy, and we will work with that later on. Okay, so you don't need to worry about that for now. We just need to know that for an ideal gas, the internal energy is proportional to temperature. Okay, and there's a proportionality constant. We'll calculate that later on. Okay, but this is good to remember for now. Okay, any questions so far? Okay, so that's the internal energy part of the equation. The next bit is looking at heat. Okay, and we've already done work. Okay, so heat, that's Q, given by the symbol Q. Okay, so heat is the transfer of energy. Transfer of energy from one body to another due to a difference in temperature. Okay, in other words, a temperature gradient. Okay, so we looked at this last time. Whenever you have a system where there's a temperature gradient, you then have heat flow from one side of the system to another. This heat flow, that's the heat that we're talking about. It's the movement of energy from the one side of a system to another because of this temperature gradient. And I'm emphasizing that it's a heat flow or transfer of energy because heat is not something that an object can have. It's not something that like you can hold. You can't have heat. Heat is the transfer of energy. So a note here, an object does not hold onto heat. Okay, so it's not something you have, it's something that is transferred. So it's like the process from going from one body to another, that's this heat transfer or energy transfer. Okay, so a little picture to keep in mind. Here we've got our system, it's going along X. We've got some temperature T. At the one end point of the system, we might have T hot. And then we've got the temperature decreasing. It doesn't have to be linear, just decreasing down to another temperature T cold. Okay, so this gives us a temperature gradient. In this case, we've got a constant temperature gradient. And we know that heat will flow from hot to cold. So it will go, Q will go that way across the system. Okay, so that's just the picture you need to keep in mind with this idea of heat. It's the energy transfer. So it's not a specific part of the system that holds on to heat. It's the motion of this energy going from one part to another. Okay. Let's have a look back at our first law of thermodynamics equation. This delta U is equal to Q, let's say plus W if we want to use this convention. Okay, now about that plus or minus sign, again, that's up to you. You can choose what you want, but just something to keep in mind. If heat is gained by whatever means, then Q is positive. Okay, gained heat is plus, right? Heat lost will be minus because we're losing heat. Okay, during compression, energy is gained in the system. So work done, so W is positive in that case. Okay, because it's gaining energy. During expansion, we've got the minus W. Okay, because then energy is lost in this expansion. Okay, so just keep this in mind when you're picking your convention. Okay, so energy is always gained when heat is added. Energy is lost when heat is taken away. Energy is gained when the gas is compressed. Energy is lost when the gas is expanded. Okay, as long as you remember those four things, you shouldn't have any issues with that plus or minus sign. Okay, any issues with this so far? Okay, one last thing. If we go back to that differential form that we had, remember that was du is equal to dq plus dw. Okay, remember the bar, that's for the process functions that might depend on the path. We can rearrange this to solve for dq, and we can get dq, again with the little bar, is equal to du plus P dV, okay, differential form of that. If we want to work out the total heat transferred for a specific process, remember a process is just that curve through the state space, then Q, the full heat or the total heat, is the integral over gamma of this differential. So a little picture to keep in mind. Let's say we've got our PV diagram again. We start at this point, we end at this point. We do some process, doesn't matter what. We integrate this differential dq over this curve gamma. And that will give us the total amount of heat transferred. So if it's plus, then the system absorbed heat, energy went up. If it's minus, then the system lost heat, the energy goes down. Okay, but that depends on the path taken and what states you end up at. Okay, but this is how we are going to calculate the heat transferred or the total heat transferred. Okay, any questions on that? Okay, so those are the equations that we're going to be working with. Now, just a little bit of extra stuff that we get along with this first law, and that is perpetual motion machines. So the first law of thermodynamics forbids a certain class of perpetual motion machines. Okay, and that's the first kind or the first class. Okay, so new section, perpetual motion machines, 1. Okay, so there's different groups or different classes of perpetual motion machines. For now, we're going to deal with this first group. Okay, so remember what we said last time, that this first law of thermodynamics is like an energy conservation law in thermodynamics. Okay, so from what you know about perpetual motion machines, you know that these are machines that go on forever. Okay, roughly speaking. Okay, more precisely, we can say the first law of thermodynamics implies that perpetual motion machines perpetual motion machines of the first kind. Yeah, so again, there's different groups. So this talks about the first group. The first kind are impossible. Okay, so that's one of the results we get from this first law of thermodynamics. Now, what is this first grouping of perpetual motion machines? Let's have a look at that. So the star, a perpetual motion machine of the first kind produces work or does work, however you want to think about it, produces work without, yeah, that's the key here, without the input of energy. Okay, so you're getting work is being done without some input of energy. It just does work by itself. Okay, so that's what it means to be a perpetual motion machine of the first kind. Okay, just a little note on that. So, note. There are 2 more kinds. of these machines that we will discuss later. Okay. Okay, so that is a little introduction to perpetual motion machines. So there's different kinds that we're going to be looking at. This is the first kind. So it does work without any input of energy. And the first law of thermodynamics says that this is impossible. Okay, so whatever machine that you want to build, if it does work, okay, like if it moves something or it turns something, does something, there has to be some input of energy. Okay, there has to be. Okay, so that is the first consequence of this first law of thermodynamics. Okay, are there any questions on this? Okay, so that's just a very brief introduction. We'll look at this later on when we do engines and refrigerators. We'll look more into this. Okay. The next big thing to go through is that of enthalpy. Okay, not to be confused with entropy, which we will cover later. So enthalpy, okay, given by the symbol capital H. Okay, so just a brief introduction. Enthalpy is a state function. Okay, so that's just a function of the state. For example, f of PV. Okay, that's a state function. Okay, defined by H of U, P, and V. So it's a state function. It depends on the internal energy. It depends on the pressure and the volume. And it's given by U, internal energy, plus PV. Okay, that's how we define enthalpy. Okay, so what do we use enthalpy for? So enthalpy is used to analyze chemical reactions. Okay, so that's some kind of thermodynamic process. So analyze chemical reactions at constant pressure. Constant pressure. Okay, in other words, isobaric processes. Okay, so at constant pressure or isobaric. Okay, to give the heat of the reaction. Okay, so you would have seen this in metric chemistry. You've got some amount of initial chemicals that you're reacting. You've got some amounts of final chemicals after the reaction. We look at the difference in energies between the two, and that can tell us if heat is given off in the reaction or if heat is absorbed. Okay, and then we can break it up into endothermic and exothermic reactions. Okay, this is what we use to do that. We use this enthalpy of the reaction. Okay, so we can write this just in terms of the function. Sorry, so the function h is equal to u plus pv. Sorry, pv. Okay, I'm just going to go through this step by step as an introduction, and then you should be able to do this for other things. But what we're going to do is find the differential of the enthalpy. Okay, so this is the total function h. We want the differential, so dh. Okay, so H is a function of several variables. So we know how to do this from Math 212, but let's just go over this again. So this is going to be the differential of U plus PV. Okay, so dH will then be du plus the differential of PV. Now we've got a product of two things. So these are functions, P and V. They're state functions. So dH is going to be du plus, we leave the first one, we take the differential of the second, dV, plus we leave the second one and take the differential of the first one. It's like the product rule with derivatives. However, enthalpy is used at constant pressure. So that means pressure is a constant, and so dP is 0. So this term goes away. Okay, because we're only dealing with constant pressure reactions. Okay, so we're left with dH is equal to du plus pdV. Okay, but notice from what we had before on heat, remember we had du is equal to dq minus pdV from taking that differential form of the first law of thermodynamics. We can take this and substitute it in. The pdV and minus pdV, they cancel. So we have dH is equal to dq. And just to emphasize that we're working with constant pressure, we put a little p at the bottom. So that means constant pressure. If we're working with constant volume, then we put a little v at the bottom. Okay, it's just so that we can see quickly what is constant and what is not constant. Okay, so here we see how the enthalpy is related to the heat transfer in the reaction. Okay, again at constant pressure. Okay, and just a note. The total enthalpy of a system cannot be directly measured. Cannot be directly measured. And so we work with changes in enthalpy. Okay, so we can't work with totals, so instead we work with the changes in the enthalpy. Much like with potential energy from first year mechanics, you can't measure the exact potential because you can always shift it up and down by a constant. So instead you work with differences in potential. Okay, and then across a certain distance, that gives you the force. Okay, but directly you can't do that. Okay, so the change in enthalpy we call delta H, and that is just going to be HF minus HR. Okay, final minus initial. Okay, so given a particular delta H, what do we know? We know that we call the reaction exothermic. So an exothermic reaction when delta H is less than 0, which means heat is released. Okay, the thing gets hot, heat is released. It is an endothermic reaction. Okay, that's when delta H is greater than 0. And in this case, heat is absorbed. Okay, so heat from the surrounding moves into the chemical reaction. So it's endothermic. Okay, so that's the difference between this exo and endo. Okay, any questions on that? Okay, then there's a couple little things that we need to know, and that is enthalpy. Enthalpy with phase changes. Okay, so if you've got a substance and it's moving from one phase to another, there's a certain amount of enthalpy related to that phase change. The first one is enthalpy of fusion. Okay, also called latent heat of fusion. So what is that? This is the enthalpy change. Right, we're always dealing with changes in enthalpy. So this is the enthalpy change required to completely change one mole of a substance from solid to liquid. Okay, so that's the first thing. The second thing, enthalpy of vaporization. Okay, so what is that? That is the enthalpy change required to completely change again 1 mole of a substance from liquid to gas. Okay, so these are just 2 examples of enthalpy that we're going to be using. Okay, enthalpy of fusion, enthalpy of vaporization. Now, this is just 2 examples with phase changes. There's many more. So you can have cases of a liquid going into a solid, a gas going into a liquid, a gas going straight to a solid, or a solid going straight to a gas. There's all these different phase changes that are possible. And with each one, there's an associated enthalpy change. Okay, and we can calculate what this enthalpy change is, okay, from one phase to another. Okay, any questions on enthalpy? Okay, so one last thing for today. I just want to introduce the idea of heat capacity, and then we'll look more into this on Friday. Okay, so heat capacity. Given by the symbol capital C. Okay. However, you won't see it as capital C because there are 2 different kinds of heat capacity, and they have slightly different symbols, and we're going to be using those. So you hardly ever see just plain capital C. Okay, so what is heat capacity? The heat capacity of a system is given by C, and it's equal to dq by dt. Okay, so what do we mean by this? dq is heat added to the system, and dt is the resulting increase in temperature. Okay, so this seems pretty intuitive. If I've got some system and I add a whole lot of heat to it, we expect the temperature to increase. This heat capacity is the measure of the relationship between the amount of heat we add to a system and the increase in temperature. So for some systems, maybe you have to add a lot of heat to get a small change in temperature, okay, like water. Or you might have other systems where a small amount of heat gives a large change in temperature. Okay, so this difference here, that is this heat capacity. Okay, and just a little note, you might see heat capacity in this form called specific heat capacity. So specific heat capacity. Okay, and this is just little c, and it's given by the normal heat capacity, as we stated there, divided by the total mass. So it's the heat capacity per kilogram of the substance. So just capital C by itself, that's an extensive variable. It depends on the size of the system. However, specific heat capacity is an intensive variable because it's heat capacity per kilogram. Okay, so it's intensive in that way. Okay, so now I said earlier that there were two kinds of heat capacity. So the heat capacity, okay, that is in two parts. Okay, so the first one is at constant volume. Okay, and we use the symbol C with the little V at the bottom to show constant volume. Okay, and then there is at constant pressure. Yeah, and then we use the C with the little P at the bottom to show constant pressure. Okay, so how do we find these two? So remember dQ at constant volume, this would be du plus P dV. But constant volume means this dV term goes away. So we're left with just du. So if we're trying to find the heat capacity at constant volume, that's dQ by dt. Then CV would then be dQ at constant volume by dt. But dQ at constant volume is du. So it's just going to be du by dt at constant volume. And this is very, very important. We're going to see this quite a bit. Okay, so big star for that one. And at constant pressure, dQ at constant pressure, you can check this. Just go back to our definition of the dQ from before. This is equal to dH, the change in enthalpy. So here, Cp is going to be dQ at constant pressure by dt. So this is going to be dH by dt at constant P. And you can work this out. This is going to be Cp is equal to du by dt at constant pressure plus P times dV by dt at constant pressure. And we will be using this quite a bit as well. Another star for that. Okay, so that's just an introduction to heat capacity. In the next lecture, we will go through examples with real systems, and then we're going to calculate these things. Okay, any questions on this? Okay, cool. So homework, not homework, sorry, the hand-in problems number 2, that's been uploaded to Learn 2022. You can start going through that, and then that will be due next week, Monday at 12. Okay, so you've got a week to do that as well. And then that will be on what we're covering this week. Okay, as always, if you have any questions, please email me, or you can post your questions on the WhatsApp group, and I can help you out. So tomorrow we will go through some of those tutorial questions. Okay, bye everyone.